All right, so we are going to begin chapter 7 with this video. So the first section in chapter 7 is titled Integration by Parts. And this is going to begin we do 5 or 6 different sections in this chapter. So before we get into what integration by parts is, one thing to note here is that there are a bunch of integration rules that we have already covered throughout this semester. So this is obviously posted on Canvas under the blank notes tab, and it's the first slide in these notes. You will need to learn all of these because throughout the rest of chapters 7 and 8, any of these could show up, and you'll need to know all of them. Also, on your next test, there is a good chance that I'm going to have you do the rules, which means that I'm going to pick a few of these at random just to see if you know them. So you need to start learning these because either on next test or so, I'm going to test to see if you know them. I'm not going to make you do all of them, but I'm going to pick out some random ones, and they're also going to show up throughout lecture as well. So as far as integration by parts goes, this is what we're going to look at. So if we wish to integrate something like the indefinite integral of x times e raised to the 2x, all of the techniques that we've covered so far would not work. U sub would not work. We wouldn't be able to cancel anything. So what we're going to do is we're going to remember a rule from Cal 1 called the product rule. So when you took the derivative of two functions being multiplied together. So if you remember from Cal 1, when you took the derivative of f times g, you would get the first times the derivative of the second plus the second times the derivative of the first. And then if you integrated the product rule, so you're trying to undo yourself, you could say that f times g is equal to the integral of fg prime plus the integral of gf prime. Rearranging this a little bit, you are going to get a formula that becomes very popular throughout chapter 7 called the integration by parts formula. And it is officially written as the integral of f times g prime is equal to f times g minus the integral of gf prime, which means when you've got two functions being multiplied together inside the integral, if you can label one of them as f and one of them as g prime, you can then find f prime and find g to substitute into this formula and then solve a new integral that's actually one of our old techniques. Now, in a lot of textbooks, they usually don't use f and g because it's a little bit confusing. So what we can actually do is that if we let f of x be our u function, and then you let g prime of x dx be your dv function, then you can rewrite your integration by parts in a little bit more straightforward way. So the way that we're actually going to express integration by parts is the indefinite, or it could be a definite integral, I guess, of u times dv is equal to uv minus the integral of v du. Where once again, if you label u and you label dv, you can use your u function and take the derivative to find du, and then you can take the antiderivative of dv to get the v's in your formula. And this would be your integration by parts. So in the end, you want it to be u times v minus the integral of v du. Now, one of the challenges that students run into here is, well, how do you know which one should be u and which one should be dv? So what we're going to look at here is a rule called limit. And this is a little analogy that people use to help remember what should you let u be. Because whatever u is, then we can default the other term to be our dv term. So limit stands for the L represents logarithms, usually in the natural case. I guess it could be the L, we'll usually do natural logs. I represents inverse trig. P represents polynomial functions. E represents exponential, and T represents trigonometric, all right? So if we go in this order from top to bottom, whichever one you run into first, we are going to let that be our u, and then the other term will be our dv term. That's the most straightforward way to set up integration by parts. So let's work that example I just showed you using this new technique. What is the indefinite integral of x times e to the 2x. All right, so when you set this up, you're going to have to label one of your functions as being your u function, and you're going to have to let one of your functions be your dv. So using the analogy of Lipit, there are no logarithms, there are no inverse trig, but there is a polynomial function. So I'm going to let u be my polynomial function, which is x, and therefore dv is going to be e to the 2x dx, whatever's left over. From there, you can go from u to du by taking the derivative, which would be dx, and then you can go from dv to v by taking the antiderivative, and the antiderivative of e to the 2x would be 1/2 e to the 2x, because that's just doing the anti-chain rule like you learned in Cal 1. When you integrate an e function, you just divide by the derivative of the power. And remember, this means that our formula for integration by parts will be u times v minus the integral of v du. So you're going to plug your pieces into this formula and see what you have. So if you multiply u times v, so x times your v function, you will end up getting 1/2 x e to the 2x minus the indefinite integral of v times du, which would be 1/2 e to the 2x, and then du is dx. You can factor that 1/2 out to the front because you don't need it, and this would be 1/2 x e to the 2x minus 1/2 the indefinite integral of e to the 2x dx. And that is something we now know how to integrate, which means our integration by parts formula worked. You would end up with 1/2 x e to the 2x minus 1/2 times the integral of e to the 2x is e to the 2x over 2. And since it's indefinite, do not forget your plus c. And then if you simplify this a little bit, you can write your final answer as 1/2 x e to the x minus 1/4 e to the 2x plus an arbitrary constant c. And that is the idea of integration by parts. Label your u, label your dv, solve for the opposites, and then plug everything into your formula. All right. Example number 2. Integrate the indefinite integral of an inverse cosine function. So we know how to take the derivative of an inverse cosine. That's just a formula, but integrating it is a little bit more difficult. So once again, we are going to label in our formula what is u and what is dv. So using Lipit, we can go from left to right here. There are no natural logs in the problem, but there is an inverse trig function. So I'm going to let my inverse trig function be my u. And then the only thing that's left over here is that dv will have to equal dx. So to get your du term, you're going to take the derivative from Cal 1, and the derivative of inverse cosine is -1 over the square root of 1 minus x squared dx. And then to get from dv to v, you're going to take the antiderivative. So the integral of dx would just be x. So don't forget, integration by parts is uv minus the integral of v du. So let's substitute everything into our formula. So if you multiply your u and v term, you will get x times the inverse of cosine minus the indefinite integral. And if you multiply your v and your du term together, you will get -x over the square root of 1 minus x squared dx. Now, if you would like to, you can factor that negative out front. I'm actually going to leave it there because I think it's going to end up canceling anyways, because the only way to integrate this function now is not integration by parts again, but now you can go back and do u substitution. So for your integral, if you let u be 1 minus x squared, then du would be negative 2x dx, and du over negative 2x is dx. So now solving this integral here, you will still have the x times the inverse cosine function minus the integral of negative x over the square root of u times my dx term, which is du over negative 2x. And just like I suspected, I can see a couple things that cancel here. The x's cancel, but also those negatives cancel. So if you brought it out to the front, it's okay. You would have to just do an extra step. But in the end, either way you do it should be fine. What I can do now is I can bring this extra 1/2 out front of my integral to make it x times the inverse cosine minus 1/2 times the integral. And if you rewrite 1 over the square root of u, that is the same thing as u to the negative 1/2 that we can now integrate. So this is x times the inverse cosine of x minus 1/2 times, add 1 to the power, which is u to the 1/2, and I'm going to multiply by its reciprocal, which is 2, and then don't forget your plus c. Well, the 2 and the 1/2 here just cancel each other, and don't forget to substitute your u function back in. So your final answer here is one of two things. You can leave it as x times the inverse cosine of x minus 1 minus x squared, all raised to the 1/2 plus c. Or remember, raising anything to the 1/2 power is the same thing as a square root. So that would just be the square root of 1 minus x squared. And that is the integral of an inverse cosine function. You see, not as pretty as the derivative was, but integration makes it a little bit more tedious. So that's how you would use it to integrate inverse trig functions. So where it can get a little bit challenging is in integration by parts, you may have to go through the process a couple of times. So how will we know kind of ahead of time if this is going to be the case? So at the top of the screen, you can see it says, if a function is raised to a power, we might have to go through the process a few times in order for this to work. So let me show you what that looks like through the next couple of examples. So what is the indefinite integral of a natural log function all squared? So when I set up my integration by parts here, you're going to use limit again. So there is a natural log function. So in this case now, since the natural log is being squared, you will have to let the whole thing be your u function. And then by default, your dv would just be dx. So when you find your derivative here to find the du, that's going to be a chain rule from Cal 1, which would be 2 times the natural log of x multiplied by the derivative of the inside, which is 1 over x dx. All right. And then your v would just be x. We can clean up du, but I'll clean up du when I actually use it here in a second. For now, I'll just leave it in this form. So once again, integration by parts is uv minus the integral of v du. So when I substitute all of my terms in, when I multiply the u and the v term together, that is x times the natural log of x all squared minus the integral of v du, which would be x times, and if I clean up my du term, that would be 2 ln of x over x dx. Now, a couple things happen here. First, your x over x does cancel, and you can factor the 2 out in front of the integral, which would make this x times the natural log of x squared minus 2 times the integral of ln of x dx. The problem is that we don't know what the integral of the ln of x is. So what you will have to do is actually go through integration by parts again for a different function here. So far so good, but now you need to do integration by parts for this. So over here, we're going to define new u's and new dv's to work this problem. So I'm actually going to do this one in green so I can keep them separated. So on this one, inside the integral, if you go through limit again, this time you're going to let u just be the natural log of x, but dv will stay consistent and just be dx. So du, the derivative of ln of x would be 1 over x dx, and then v would just be x. So when I go to rewrite over here in purple, this would be x times the ln of x all squared minus 2, and then you're going to do the same formula for integration by parts, but with your new information. So if you do u times v again, you will get x times the natural log of x minus the integral of v du, which is x times 1 over x dx. And if I were to distribute this 2 and clean this up a little bit, you will end up with x times the ln of x all squared minus 2x times the ln of x. Now inside the integral, the x's cancel, but when you do a negative 2 times a negative integral, it becomes plus 2, and then you're just integrating the dx that's left over. So that's something really easy to integrate, so let's take care of that. This would be x times the ln of x squared minus 2x times the natural log of x plus 2x, and then don't forget when you're finally done integrating to put a plus c on the end. And that's an example where you have to go through integration by parts more than once, and that will happen when you have a function being raised to a power where integration by parts is necessary. Now, this can also happen when you have, once again, you can see in this one, you have the indefinite integral of x squared times a cosine function. What gives away to me right here that I might have to go through this a couple of times is that x is being squared. The cosine is not the problem. It's the x squared that's going to make us do this more than once. So when we set up our integration by parts for number 4 here, remember going back to limit, there are no logarithms. There's not an inverse trig, but there is a polynomial function. So for your u, my polynomial function is x squared, and then the remaining terms, the cosine of x dx, will be your dv term. Finding each of their opposites, the derivative of x squared would be 2x dx, and then the antiderivative of cosine would be sine. And once again, you're going through the process of integration by parts, so uv minus the integral of v du. If I multiply the u and the v term together, you will get x squared sine of x minus the indefinite integral of v du. And multiplying those together would be 2x sine x dx, which then I don't really need that 2 here, so I could factor the 2 out front and make this x squared sine of x minus 2 times the integral of x sine x dx. And when you look at that new integral that you picked up, it doesn't look much different from the original where you've got a polynomial function times a trig function. So we don't know how to integrate that directly, so you're going to have to go through integration by parts again to simplify this second integral. So you're going to have a new u and actually a new dv in this problem as well. So with x sine x, there are still no logarithms. There is still no inverse trig, but you still have a polynomial function, which is x. That will be your u. dv will be the trig function, or what's left over, which is sine x dx. And then finding each of the opposites. Du would be dx, and then the antiderivative of sine is negative cosine. Substituting those into my new integral, you will have x squared sine of x minus 2 times your second integration by parts. So u times v would be negative x cosine of x minus the integral of v du, which is negative cosine of x dx. Now, the integral of positive cosine is way easier to do, but it doesn't matter. You could leave the negative. So just to show you, you can either factor the negative out front and make it positive and integrate cosine, or if you're comfortable integrating negative cosine directly, that's fine too. So I'll actually do that just to show you it doesn't matter. So x squared. So if I multiply the negative 2 through, it would be a plus 2x cosine of x. All right, and then you would have a plus 2 times the integral of negative cosine x dx. All right, so now you can integrate negative cosine. So this would be x squared sine of x plus 2x cosine of x. The antiderivative of negative cosine is negative sine, so you actually just get minus 2 sine x, and then don't forget your plus c on the end. This is your integration by parts twice for the original problem. So anytime you have a function being raised to a power in your problem and you have to do integration by parts, the number of the power is usually how many times you will have to go through that process. But the good news is that that is not always necessary. So the last two problems we did, one of them, the second one we did, actually could have been done in a little bit better and a little bit more productive way. So there is actually a technique that our textbook doesn't talk about, but it's very simple to learn, and it's something that I'm going to teach to you. It's called the tabular method of integration by parts. And let me read through this paragraph I kind of typed out for you. While the aforementioned recursive definition is correct, it is often tedious, as you saw, to remember and implement. A much easier visual representation of this process is often taught to students and is called the tabular method. This method will work best. Now, here's the key. This method works best when one of the two. So if you go back to the two problems we did, x squared had a polynomial function as our u. The first one had a natural log. This first one we did is probably not a good candidate for tabular method. So actually the way we did number 3 is probably the better way. This one though, we're going to work this problem again and show you how you can get the exact same answer. So wanted to mention that first. This method works best and easiest if one of your terms is a polynomial. The reason that it's so nice is because after you take the derivative of a polynomial function several times, eventually you want that derivative to go to 0. A derivative of a natural log function doesn't ever go to 0, which doesn't really help. So that being said, I wasn't going to type up what you have to do. I think it's going to be best if I do this by explanation. So let's revisit x squared cosine x, and let's see if we can get the same answer doing tabular method of integration. So what I usually do is I take my polynomial function and I put it in one column and I put my other term in the other column. Since the polynomial derivative will eventually go to 0, down the first column, you want to take as many derivatives as it takes until eventually you get to 0. So the derivative of x squared is 2x, 2x becomes 2, 2 becomes 0. Those are all derivatives, which means you have to go the opposite direction for the other function. So the antiderivative of cosine is sine. The antiderivative of sine is negative cosine, and you do it as many times until you get to 0. The antiderivative of negative cosine is negative sine, and you stop. But since there is a minus built into the integration by parts formula, over here on the left next to all of your derivatives, you need to alternate signs all the way down, always beginning with positive. And then you are going to multiply at the diagonal all the terms that you can. Now, you don't need to do the 0 because obviously after that point, everything else goes away. And then you write down your multiplication terms. Positive x squared times sine is x squared sine of x. Negative 2x times a negative cosine is positive 2x cosine of x. And then positive 2 times negative sine is negative 2 sine of x. And then don't forget your plus c because it is indefinite. And that is the exact same answer that we just got on the previous problem, but I never had to do integration by parts. Once again, this method of tabular will only work if one of your terms is algebraic and it goes to 0, and the other term is something that is easy to integrate. If you have a logarithm or an inverse trig, this will not work. You will have to do it the other way. It's best set up if you have a polynomial times a trig function or a polynomial times an exponential function. Those two work the best, and that's when I usually do a tabular method. So let's do a couple examples of where we can work out tabular method by hand. So what about this one? It's also going to be our first example of a definite integral. So what is the integral from 0 to 2 pi of t squared times the double angle of sine? Now, when you look at this, there is a polynomial function, and this is a trig function. That is a good setup to do tabular method instead of having to do integration by parts. So just like the previous problem, I'm going to set myself up a little chart here where I'm going to put t squared in the first column and sine of 2t in the second column. The first column, take derivatives until you get to 0, which is 2t, 2, and 0. And then in your second column, you're going to do a bunch of anti-chain rules to get all of your antiderivatives. So sine of 2t integrates into negative 1/2 cosine of 2t. Remember, take the antiderivative of sine, that becomes negative cosine, and you divide by the derivative of the angle, which is 2. Do it again, and you should get negative 1/4 times the sine of 2t. And then one more time, it should become positive 1/8 times the cosine of 2t. Go over to the left, and you need to alternate your signs. That way you're taking care of the negative that's in the integration by parts. And then you are going to multiply at the diagonal to get your final result. So positive t squared times negative 1/2 cosine 2t should be negative 1/2 t squared cosine of 2t. All right, a negative times a negative makes this plus, and you should get 1/2 t times the sine of 2t. And then 2 times an eighth gives me a 1/4 times the cosine of 2t, and we're going to evaluate this from 0 to 2 pi. So take your integral that we use tabular method on, and let's plug 2 pi into everything. So this would be negative 1/2 times. If you square 2 pi, you get 4 pi squared. And then the cosine of 4 pi is actually 1 plus 1/2 times 2 pi. The sine of 4 pi is 0, so that term will go away in just a minute. Plus 1/4 times the cosine of 4 pi, once again, is 1. Minus When you plug 0 in, do not jump to the gun that you think everything will cancel, because it cancels a lot of this, but not everything. The first term it does cancel because t squared would become 0, so that whole term becomes 0. There's also a t in the second term, so that second term also becomes 0. But in the last term, the cosine of 0 is actually 1, and 1 times a fourth is going to be a fourth. So let's see, these zeros are not really here. This second term in the first parentheses is not really there. And if I simplify everything else, negative 1/2 times 2 pi squared is negative 2 pi squared. Then you get a plus 1/4. And when you distribute this negative through, it becomes a minus 1/4, which that's nice. They cancel each other and give you negative 2 pi squared. And that is your final answer for this definite integral. And that is how you would work tabular method, but tabular method could also be done with a definite integral. If it wasn't definite, you would just stick a plus c after you did the tabular method. So let me do one more tabular method that go back to indefinite, so you can just do a plus c. Hyperbolic trig or hyperbolic functions. We haven't looked at those in a little bit, so let's bring that back. So I want you to take the integral of y times the hyperbolic sine of 2y. So in this case, you have two functions. You have a polynomial function, which is good, and hyperbolic trig can just be kind of lumped in with your trig functions because they will work very similar here. So since you have a polynomial times a trig function, this can be done using the technique of tabular. So we're going to start off with y in my first column, and you're going to take the derivative until you eventually get to 0. So that would be 1 and then 0. You can integrate hyperbolic sine using the anti-chain rule. So you should get 1/2 hyperbolic cosine of 2y on the first time. In the second one, you'll get 1/4 hyperbolic sine of 2y. We will alternate our signs down, and then we will multiply at the diagonal to get our final answer. So the first two products, you'll get 1/2 y times the hyperbolic cosine of 2y, and then minus 1/4 times the hyperbolic sine of 2y. And since it's indefinite, we will put a plus c on the end. So there's another example of doing a tabular method instead of having to do integration by parts. But once again, this only works when you have a polynomial function times trig or a polynomial function times exponential. If anything else pops up, you will have to do integration by parts. So I will show you with this problem. This is a very popular problem that we give all the time in our Cal 2 classes because students try to do tabular method and you run into a giant issue. So for this first part, just listen and watch what the issue is. If you try to do tabular method, it's not that you can't take the derivative of t to the fourth. I'm not worried about that. But integrating ln of t over and over is not very easy because you would have to then do integration by parts inside of your tabular method, and that's not worth doing. If you have to do integration by parts to do tabular, you might as well just do integration by parts from the beginning. So I'm going to erase this. So we're not going to do tabular method. Instead, we're going to go back to the problems we did earlier. We need to define what our u and our dv term are. Once again, using the idea of Lipit. Since there is a logarithmic function, I'm going to let that be my u, so ln of t. And then everything else, the t to the fourth and the dt will become my dv term. I can find du, which is 1 over t dt. And then I can find v, which the antiderivative would be 1/5 t to the fifth. And since we're not doing tabular, we'll go back to the formula uv minus the integral of v du. So when I multiply my u and my v term together, you will get 1/5 t to the fifth times the natural log of t minus the integral of v du, which is 1/5 t to the fifth times 1/t dt. Two things happen with this integral here. Number one, this t cancels one of those t's to make it t to the fourth, and this 1/5 you can just bring out in front of your integral. And this will be 1/5 t to the fifth times the natural log of t minus 1/5 times the integral of just t to the fourth dt. We know how to integrate t to the fourth, so that's just adding 1 to the power and dividing by the power. So you would get 1/5 t to the fifth times the natural log of t minus 1/5 times, that would be t to the fifth over 5 with a plus c. And then if you combine your constants here, the final answer would be 1/5 t to the fifth times the natural log of t minus 1/25 t to the fifth plus an arbitrary constant c. And that is your final answer. Just please be careful because this would not be a tabular method because there is a natural log in the problem. So please be careful. Tabular method does not work for every issue. All right, and then to wrap this problem up, this section up, the only thing that we have not covered so far is what happens when you do integration by parts, but you make it all the way to the e in Lipit. We haven't talked about that, and that's going to actually cause a new issue to arise that we're going to talk about. So the example I want to use to show you this idea is what is the indefinite integral of e to the negative x times the double angle of cosine. So when you use Lipit to determine what your u should be in integration by parts, there are no logarithms, there's no inverse trig, there are no polynomial functions, you make it all the way to e. So therefore the e to the negative x is actually going to be your u function here, and your dv would be the double angle of cosine dx. Find their opposites. So du would be negative e to the negative x dx, and v would be 1/2 the sine of 2x. We're still doing integration by parts, so uv minus the integral of v du. So when I multiply the u times the v, I would get 1/2 e to the negative x times the sine of 2x minus the integral of v du, which is 1/2 the sine of 2x times a negative e to the negative x dx. So the only thing I can really do with this integral is I can bring out that negative and that 1/2 to the front, and that will make it 1/2 e to the negative x times the sine of 2x minus, it'll actually be plus 1/2 when you bring the negative out front. So plus 1/2 times the integral of e to the negative x sine of 2x. So you see what happened here was the only thing that changed is that our integral went from a double angle of cosine to a double angle of sine. So it looks almost the same. All right, well, that doesn't help us at all. I don't know how to integrate this still. So therefore, we're going to have to end up doing integration by parts one more time, just like we saw a little bit earlier. But we didn't really know that ahead of time because there was no powers here. So if I do integration by parts for this integral here, so we're going to once again define our u. So if you go through limit again, you will still have e to the negative x, but this time our dv needs to be the double angle of sine. Your du is going to be the same term. It's negative e to the negative x dx. And then v is going to be negative 1/2 times the cosine of 2x. So you need to substitute another integration by parts into this little green bracket here. So you will get 1/2 e to the negative x times sine of 2x plus 1/2 times. Do integration by parts again. So u times v would be negative 1/2 e to the negative x times the cosine of 2x minus the integral of v du, which is negative 1/2 cosine of 2x times negative e to the negative x dx. All right, so inside of your new integral, you could cancel the negatives because this negative and this negative cancel, and you can actually bring that 1/2 out front. And this would make it 1/2 e to the negative x times the sine of 2x. I'm also going to do another step. I'm going to go ahead and take this 1/2 and distribute it to both terms. So it would make it a minus 1/4 e to the negative x cosine of 2x. And then you would have a minus 1/4 in front of the integral. So when you factor the 1/2 out and you multiply it by another half, and then inside your integral, here is where the fun starts. You are now going to have exactly the same thing that you started with. This is what's called cyclical integration. If you do integration by parts twice and you get back to what you originally have, it's not going to be worth going any further. But that doesn't mean you can't solve this. What this now means is that if this 3 parts came from integrating the original function, then that means that these 3 terms have to equal the original problem. And now what we're able to do is set up an algebraic integration problem. Because now that I have the same integral on both sides of the equal sign, I could add the 1/4 integral to both sides. And you're essentially treating the integral like a variable. That way you can actually combine these 2 terms. When you do that, this cancels on the left, and you are left with these other 2 terms come down. 1/2 e to the negative x sine of 2x minus 1/4 e to the negative x cosine 2x is going to equal. And if you have one integral plus 1/4 of an integral, you will pick up 5/4 of the same integral of e to the negative x cosine 2x dx. And now remember, the original problem asked you to get the integral by itself. So now that you've combined 2 integrals into one, you can get the integral by itself by multiplying both sides of the equation by 4/5. Because 4/5 times 5/4 is going to cancel. And we can say that the indefinite integral of e to the negative x cosine 2x will be 4/5 times 1/2 is going to end up being 4/10, which is 2/5 e to the negative x sine of 2x. And then 4/5 times a negative 1/4 would actually cancel the 4's and give us a minus 1/5 e to the negative x cosine of 2x. And then now that we know it's an indefinite integral, you can now add a plus c onto the end and this is your final answer. And that is an example of a cyclical integration by parts. That will always happen when you have a trig function and an exponential function being multiplied together at the end. Go through integration by parts twice, and then set up an integration algebra expression and solve. So that ends the video for 7.1. You see the problems get a little bit longer in this chapter. In the next video, we will talk about different techniques to attack when you have multiple trig functions being multiplied by each other.